Hi everyone, so welcome to ACE Online by ACE Engineering Academy, myself Khadar Basha, and today here we are going to see an important topic in the point of SSC JE or RRB JE examination point of view, and how the questions we are getting, and most of the questions in DC machines, particularly if you talk, and we have questions mostly on types of DC machine, directly KVL relations for different types of machines like shunt, series, compound. So they are asking directly some questions based on KVL. Some of the voltages in a loop is 0. So by applying that KVL, we get some equations for generators and motors. Now that we have to observe. And what is these equations? So direct calculations, very easy questions we are getting. The first thing is most of the students will not have clarity in that types first. How many types we have and how it is divided, and main problem is in the compound machine. Everyone knows mainly there are two types of DC machines. One is separately excited and second self-excited. Again in self-excited we have three types: shunt machine, series machine, compound machine. So these types you should have a clarity first. Mainly in the compound machine we should have clarity. Compound is mainly two types: cumulative and differential. Again cumulative is divided into three types. Cumulative we can get in three different models, that is we call over compound, flat compound and under compound DC machines. And based on type of connection, how we connected that field windings, based on that we have three types again. We have two types again based on the type of connection. They are short shunt and long shunt. Long shunt compound machine, short shunt compound machine. So mainly two types only, cumulative, differential. Again cumulative three types: over compound, flat compound, under compound. And how to get that over, flat, under, so briefly we will see here. So I will give some information regarding how to get these three types of compound machine in cumulative compound. Okay. So first, in the types of DC machines, how many types we have? There are mainly two types. What are the two? These two. First one, separately excited DC machine, and second, self-excited DC machine. Two types we have, and based on what it is categorized, the main thing is based on these two types is divided based on excitation of field winding. It is based on excitation of field winding, excitation of field windings. There are two types. So these two are this. How we are giving excitation? Generally in DC machines, whatever the poles are there, these are electromagnets, not permanent magnets. So electromagnets means it requires some excitation or some supply we have to give to field winding, DC supply, to create the required flux. And in which way we are giving that supply to field winding? That is, already the DC generator, if you take, output of DC generator is DC voltage only. And if you give the same DC voltage to field winding back, that is called self-excited. But if we don't use the output of DC generator, and if we use some other DC voltage source to the field winding, that is called separately excited. If the field winding excited by a separate voltage source or external DC voltage source, that is called separately excited. Or if we given whatever the output voltage we are getting from DC generator, same voltage we given back to field winding, then it is self-excited. And in that self, again we have three types. What are the three types of self-excited? In self-excited there are three types. Self-excited DC machine. We have three types in this. They are DC shunt machine, DC shunt machine, and second DC series machine, DC series machine, and third DC compound machine, DC compound machine. So based on what these three we categorized is, self-excited means the supply to field winding is given from same armature, whatever the output of DC generator we are getting, same voltage we are giving back. And how we connected or how it is excited? By connecting in parallel, shunt machine; by connecting in series, And compound means here we have two field windings, both shunt and series field windings we will place in the compound machine, both excited from same armature. Now based on that how we connected the two field windings, again different categories we have. So that we will see in the compound machine separately. Now let us see first separately excited DC machine, how it is excited and what is the equivalent circuit and what is the KVL of the separately excited DC machine. Let us see this. This is the first one, separately excited DC machine. Separately excited DC machine. So in the name itself, the field winding is excited with a separate voltage source here. See here how it is. Now let us consider these are the poles and there is a field winding on this. This is the field winding on the poles, and this field winding we need to give some supply. If we give a separate DC voltage source, external DC voltage source, let some VDC. Now a current will flow in this field current IF, it is field current IF. Now whenever there is a current based on right hand thumb rule, what is the right hand thumb rule? If the thumb indicates current direction, four fingers indicates flux direction, or if the four fingers indicates current direction, thumb indicates flux direction. Okay, vice versa it is. Now here this is a current, current is circulating like this. Now flux is in upward direction, the flux is moving in this direction. This is the direction of flux. So if this is the direction of flux means here there must be a north pole and here there must be a south pole. So north to south flux direction is this. Okay, and this is our armature. I am considering it is a generator. Generator means we need to rotate with a prime mover in some direction at a speed n. Now whenever it is rotating, there is an armature winding inside the rotor or armature core we call. Now this armature winding will cut the flux, whatever it is passing here, then an EMF is induced here, and that EMF we will take outside through these brushes. Whatever EMF induced, it will come to the load. Once we connect a load, a current will flow, armature current, and EMF induced EG, and here terminal voltage is V. Terminal voltage is V. So this is our separately excited directly machine representation it is. Directly machine. Field winding, separate voltage source. Whatever the output we are getting DC, this is we are not giving back to field winding, it is separate, this is separate. Both windings are isolated windings. So there is no electrical connection between this field winding and this armature winding. So both are separated here and excited with a separate voltage source to create the required flux here. Once flux created, whenever we rotate at a speed n by using a prime mover, EMF will be induced in armature, and whenever we connect a load, a current will flow and we get some terminal voltage across the load. Okay. So this is direct machine representation. Now how this machine representation we converted to our electrical equivalent. So every time we cannot draw these diagrams, no? That's why these machines we represent in the form of equivalent circuit. The electrical equivalent of separately excited is like this. So here field having separate voltage source VDC, this is the field current, flux is developed, and whenever armature is rotating at some speed n, some EMF will be induced here EG, and whenever load is connected, load, a voltage will be appear across the terminals called terminal voltage or full load voltage whenever load is full load. Now a current is passing here IA. There is some armature winding resistance RA. Now here we need the KVL equation, or what is the sum of voltages in the loop according to KVL? 0. So if you apply that, so this is EMF induced and this is the loop here, and always the EMF induced is EG, but same voltage we never get at the load side. Some voltages will be dropped. So according to this KVL, the EMF induced is equal to output voltage plus drops. What are the drops here? Current is passing through winding, so armature resistance drop will be taking place, plus same current is also passing through brushes, through this brush. So brush is made up of carbon, which is having high resistance, definitely some voltage drop will be there, that is called brush drop. Now V plus IARA plus brush drop. This is the KVL of separately excited generator. So if it is motor also, you can write equation. If it is motor, so we don't connect load. Motor means what? So I'm not giving again separate figures for motor, so you can write yourself directly. So for motor, what we can do is, this is same field winding, and to the armature we give one more DC supply. Some other DC supply we give, different, both are not same. So this is some other DC voltage source, this is some other DC voltage source. So voltage we apply here. Then current will flow in this direction, and as DC motors are self-start, motor starts rotating. Whenever it starts rotating, you can also observe in this diagram, once we given supply here, current will flow in this direction, motor is taking the current. Then as DC motor is self-start, now it starts rotating. Whenever this rotor starts rotating, there is a flux here, north to south. Now this armature will cut the flux again. This armature winding will cut the flux. Some EMF will be induced in that. What is that EMF we call? Back EMF. Why? Because according to Lenz's law, the EMF induced in this armature will oppose the cause. Because what is the reason for EMF induced here? Rotation. As armature is starting rotating, EMF induced. Why it is rotating? Current carrying conductor you placed. Why current is passing in this conductor? Because we given some supply here. As we given some supply voltage, current is passing. So finally, the effect is EMF. The cause for this is supply voltage. So this EMF, according to Lenz's law, should oppose the cause, that is supply voltage. That's why we name that EMF as back EMF. It is in opposition to supply voltage always. So that is very important in motors. In every motor, the back EMF is very important, because if there is no back EMF, we cannot run the motor. Why? Because if there is no back EMF, very high current will flow in armature. Because of that very high current, windings will be overheated. Finally, complete winding burns here. That's why we should never operate whenever the back EMF is 0. So at which condition back EMF 0, tell me? At which condition back EMF is 0? So back EMF is 0 under two conditions. One is starting condition. Just supply given. Motor about to rotate, still it is not rotating, just about to start. At that time speed 0 only. At speed 0, as it is not rotating, it won't cut any flux, no EMF induced, EB is 0 there. But once armature starts rotating, it will pick up the speed. So back EMF also increases, because more the relative speed, more EMF will induce in the conductors. So EB will induce. Whatever EMF induced here, that EMF will oppose the cause. Because of that EMF, current passing through the armature winding is limited or reduced. Okay. So like this, that back EMF in motors will limit the current always. And that is one condition where back EMF is 0, starting. Another condition where back EMF is 0 is blocked rotor. That is, you take best example, your labs. We do brake test generally on the motors, brake test. Now you keep on apply the brake is nothing but load is applied. Now you keep on tight the belt such that up to the motor stopped. That is called blocked rotor. So in induction motor generally we do that blocked rotor test, but not in DC motors. So here in DC motor, if you block the belt tightly, the rotor is blocked and it won't rotate, then also back EMF is 0. At that time also very high current will flow in the armature. So these are the two conditions where armature current will be very high in DC motors. Okay, starting condition and blocked rotor condition. Clear? So for motor, if it is a DC separately excited DC motor, so for generator I written here, if it is motor, just cross verify your equation. If it is motor, same figure, here we give supply by removing this load. Then the KVL is supply voltage equal to the back EMF induces plus drops in that, IARA plus brush drop. Generally brush drop will not be given in most of the questions. Whenever it is not given, we will take EB plus IARA. So only this equation we take. Okay, this is for motor. Just this EG and V will interchange. Okay, don't confuse in generator equation and motor equations. In case of motor, EB will be V minus IARA, but in generator EG will be V plus IARA. Okay, here this is the input voltage, output voltage is this. But here, in case of motor, what is the input voltage? Supply voltage we give, no? V. This is our input voltage. Some EMF will induce, that is as we treat as output voltage plus drop in that. Okay, remember like this, it is easy to remember these equations. This is for motor and this is for generator. So this is about separately excited DC machine. Now let's see self-excited. In that first one we have shunt machine. The first one in separately excited is DC shunt machine. Let's see this. Let first one DC shunt machine. DC shunt machine. Now how we excite the field winding in case of shunt machine is, observe here. Same procedure, the field winding on the poles. Previously we excited with a separate voltage source. Now see what happened. Like this. Now previously we have separate voltage source here. Both the windings are isolated. But right now in self-excited, the field winding or armature winding are not isolated. They are electrically connected. And how they are connected? If they are connected in parallel, that is we call shunt. So if you want shunt machine, now excite this field winding in parallel or connect this field winding in parallel with armature like this. See here. The field winding is excited in parallel with armature and this is rotating at a speed n. Okay, this is shunt. But here in all these self-excited DC generators particularly, we have some conditions. If that conditions are satisfied, then only you will get voltage in these generators. Otherwise no voltage. The main reason is, for example, you just observe here. We know that from EMF equation, EMF Eg proportional to product of speed and flux. What is equation of EMF? Z phi n p by 60A. Z phi n p by 60A. So in that remaining terms are constant except these two terms. These are variable, speed and flux. And mainly the EMF in generators depends on these two parameters. See, out of these two, if any one parameter is 0, the EMF will be 0. If any one parameter also 0, the EMF will be 0. Right now, we have the speed, we are rotating. With a prime mover, we are rotating. But what is the flux here? 0. Why? Because what is the field current initially? 0. Why? No voltage is there here first. There is no flux, no. Because in previous separately excited, what happened? We are giving separate voltage source to field winding. Then, because of that separate voltage source, field current is passing, flux develops. Whenever we rotate, EMF induced. But right now, EMF 0 initially. Then who will supply current to field winding? That's why there are some conditions. In that, the most important condition is residual flux. Every self-excited generator should have a small amount of flux initially. That is called residual. So due to that residual flux, so that will be a small flux here. Even the field current 0, a small amount of flux is passing between the poles. That is residual. So this residual flux is due to the property of retentivity. What is that retentivity? In a magnet, even the field current is 0, electromagnet, even the field current is 0. There will be some small amount of flux for some time. That may be 10 days or 20 days or 30 days, depends on strength of material. But immediate it is not 0. Okay, that type of materials we have to choose for the poles here. A good material. So that even the field current 0, for some time that flux will be there. That is approximately 5 to 10% residual, small one. So due to that residual flux, once we start rotating, EMF will be induced here. EMF will be induced. Small amount of EMF will be induced initially. A small voltage will be there. Due to that small EMF, a current will pass now in the field winding because a closed path is appeared across the field winding. So I will show that figure also. Observe. This is machine representation and this is electrical representation. Electrically, we represent like this. Shunt field, more number of turns. Observe here. This is shunt field, and even it is open, no problem, because initially whenever we start rotating, a small amount of EMF induces small voltage, residual voltage we call, due to residual flux in this. Now here there is a path for current. When there is a small voltage also, a closure path is up here. That's why immediately small currents will flow here, ISH. Let ISH1, a small current initially. Now due to that small current, as current is passing through the field winding, now there is a current here in the field winding. When there is a current, now flux starts develops, north south. Now poles will form, a flux will develop here. A flux generated. Now due to that small field current, small flux is developed. And what is overall flux now? Already there is residual flux. Now there is extra field flux due to that field current. Overall flux added, no? So overall flux increase. Whenever flux increases, the EMF of generator also increase. So previously residual voltage, now that residual voltage slowly step by step increases and it will reach to rated voltages after saturation. So this is the process, that is a complete different topic, conditions to build up voltage in self-excited generators. So here I am giving only the figures, equivalent circuits and KVL equations of every machine. So just brief idea given how the voltage will build up in self-excited generators. Now this field current increases up to saturation of these poles, and this finally flux become constant. After saturation, this EMF also constant. And whenever we connect a load here, load, some terminal voltage will be appeared, and this is the load current and armature current here. The electrical equivalent of this is this one. Now whenever load is connected, now this is load current and terminal voltage across the load is V, terminal voltage, and this is our armature current. Now if you apply KCL at this point, first of all, what is voltage at this point? This is EG, EMF induced in armature is EG inside, EMF induced in armature. So once it is coming outside the brush, we get a voltage of V. So this is terminal voltage, just line extended, no? This voltage V, same voltage will appear here. Now that node voltage is V. And if you apply KCL at this point, sum of incoming currents equal to sum of outgoing currents, we get IA equal to IL plus ISH. Okay. And what is ISH here? This is RSH. The field current ISH equal to voltage across this voltage also same, V only it is. So the field current ISH is equal to V divided by RSH. Field current ISH equal to V by RSH. Okay. So these are some important equation. Now let us see what is the KVL here across this. EMF induced, the KVL is EMF induced is EG equal to V plus IA RA plus brush drop. But only this IA will change here. The value of IA is IL plus ISH again. IL plus ISH, and this is the ISH, V by RSH it is. ISH equal to V by RSH. Okay. So this is the electrical representation. So here one important question is, tell me how to represent shunt field winding. Important. Anyone? How to represent shunt field winding? Generally shunt and series we will have some different representation. Shunt field winding we represent with more number of turns and thin wire. Series field we represent with less number of turns but thick wire. What is the reason for this? Shunt field representation. This is represented with thin wire, and it is having more turns in this. This is having more turns. So this is representation of shunt. The simple reason here is we need the field resistance RSH must be high value. Why it is high is, as we are exciting this field winding by connecting in parallel with armature, at the same time load also in parallel with armature, load resistance will be generally low values in the range of 2 ohm, 3 ohm, 5 ohms, 10 ohms, in that range will be there. If you have this resistance also very low value, then most of the current will divert towards field winding, then load will suffer with that. So to avoid that problem, simply we will keep high resistance here. For that high resistance, the wire should be thin one, and it is more turns. More turns means already the length of the wire increases, resistance will increase. So these are some reasons why we use this thin wire and more number of turns. Okay. So this is representation of shunt field winding. If it is a motor, so I am not drawing again for motor, so write yourself. If it is a motor, remove this load here, give supply voltage V. Once voltage given, same current IL will flow in this direction, IA direction also reverse, but ISH same only for motor. Then IA will be IL minus ISH in case of motor, and KVL will be V equal to same EB here plus IARA plus brush drop. So that you cross check your equation after writing this same figure with motor. Okay. So this is about shunt machine. Now let us see the second one in the self excited is series machine. How it is excited, series. Second one, DC series machine. Second, DC series machine. Now see how we connected here. So here the field winding and armature winding both connected in series like this. Like this we connect. Observe here, armature winding and this field winding both are connected in series, or the field winding excited from armature only by connecting in series. Now like this we connect. So here whenever load is connected, then current will flow, and based on magnitude of current, whenever current is passing in this, based on magnitude of current, flux will generate. Based on the flux, EMF will generate, let EG it is, and terminal voltage across the load is V it is. Terminal voltage across the load. Okay, so this is direct machine representation, series machine, series generator. Series motor means you have to remove this mechanical input and remove this load here and give electrical input. Now same machine will behave as a motor. Same, whether it is generator or motor, machine representation will not change, only current directions will change there for generators and motors. Now what is the electrical equivalent of this? Let us see this. The electrical equivalent. The field winding connected in series with armature like this. This is the field winding connected in series with armature. Load connected. This is terminal voltage V, current IA. So here load current, armature current, field current, everything is same. And how to represent series field winding? It is important again. How to represent series field winding? Series field winding is represented with less number of turns and thick wire. Why it is as this field winding excited in series with armature, no? So this is load having some load resistance. If this resistance is very high value like shunt resistance, so shunt resistance generally in the range of 100, 150, 200, in that range will be there, very high value it is. But if you put the same value of resistor here, like 100 ohms, whenever current is passing, some 10 amps of current and 100 ohms, means so much of voltage will be dropped here itself. So much of voltage will be dropped. Then what is the voltage going to the load? Very, very less. Our regulation will be very high here if resistance is high. So much voltage fluctuations will be there if this resistance is very high. That's why we keep this resistance low value. For that reason, it is made up of, series resistance is made up of low resistance. It is made up of low resistance. So how to get low resistance? Thick wire. It is made up of thick wire and less number of turns. Thick wire and less turns, so that length reduces, resistance also reduces. So for that reason we use, and here EMF induced is EG. Then what is the KVL of this? KVL. So here Eg equal to V plus same current passing through both armature resistance and series resistance, Ia into Ra plus Rsc plus brush drop. So if you neglect that brush drop, this is the equation, KVL equation of series generator it is. Now if it is a motor, you remove this load here, give supply to this, and V equal to EB, in motor EMF is EB, plus same drops will be there, whether it is generator or motor, drops are same, no change. Okay. Now this is about series machine representation. Important is this representation of series and shunt here important. So while drawing shunt, you have to draw more turns with a thin wire, and here thick wire with less turns. Okay. Next. So this is second one in the self-excited DC machine. And what is the third one? DC compound machine. Now third one is DC compound. DC compound machine. So there are mainly two types here. Cumulative, differential. Again cumulative is three types: over compound, flat compound, under compound. Okay, cumulative it is. And how to get this cumulative three types is by adjusting the field currents. Field current of mainly series, by adjusting that by observing no load voltage and full load voltage. Based on this no load, full load voltage concept, we have three types it is: over compound, flat compound and under compound. Okay. So first in DC compound machine, compound means here we will use both field windings, shunt field and series field. So first of all, where we have the field windings? On the pole core. So field pole having two parts, the upper one is called pole core and this bottom one is pole shoe it is. Generally the field winding will be there on the pole core. Now in this compound machine, we place two field windings on the same pole. So we use both shunt and series field winding. Shunt plus series field winding. Both we will use in this. Both we are using shunt and series field winding. Now both excited from armature. So as there are two fields, shunt and series. If the two fields are added, then we call it is cumulative compound. If the same two fields are subtracted, then we call it is differential compound. So based on this, we have two types. First one, cumulative compound DC machine. Based on the magnitude of fields under the pole, addition or subtraction. Based on the two types, cumulative compound DC machine. Next, second one is differential compound DC machine. Differential compound DC machine. So here itself I am representing what is meaning of cumulative. When we get cumulative is, if the two fields are added under the pole, phi sh plus phi sm, that is called cumulative. If the two fields are subtracted, that is both are flowing in opposite direction. Suppose shunt is coming down, series is moving up, then the flux under the pole will be subtractive nature. This is called differential compound. And how to achieve this cumulative and differential? Simple one. If you want cumulative compound, let us arrange the two field windings such that both field windings carrying current in same direction. If the current is moving in the windings in same direction, both will produce the flux in same direction. Then under the pole, the resultant flux will be added or increases. That is called cumulative. So we have to arrange that. The two field windings should carry current in same direction. If the same two field windings carry current in opposite direction, then we will get differential compound. Okay. So this is based on field current direction. Clear up to here? This is based on field current direction. Okay. Next, one more is how these two field windings we connected. Cumulative three types. So that I will show you at the last, how to get the three types of compounding: over compound, flat compound, under compound. Now, based on how these two field windings connection. Based on connection, how the two field windings we connected with armature, whether it is long shunt connected or short shunt connected. So there are two types, see here. So this is long shunt. There are two types again. One is long shunt connection, and second short shunt connection, long shunt and short shunt. So whatever you are looking here, figure is long shunt it is. So this is just based on physical appearance of the shunt connection. If you connect the shunt field across both armature and series field winding, both are included in this. This is armature and this is series field, both included under shunt. This is called long shunt. Now what is short shunt is, like this will be there. In the short shunt, the shunt field is connected directly across armature only. Directly across armature, like this. So this is short shunt. Observe here how the shunt looks, short one only. No? Here the shunt looks short, here the shunt looks long it is. If the shunt field is connected across both armature and series field winding, this is long shunt. And here short shunt, it appears as a short shunt only. This is a short shunt. Okay, shunt field is across armature terminals only. If it is connected across both armature and series field winding, that is long shunt. Now, out of this, anything may be cumulative. So, long shunt you can design cumulative compound, differential compound, and this is also either cumulative or differential, like that. Now, previously I said this cumulative compound we divided into three types. It is divided into three types now again. This cumulative divided into three types. They are over compound DC machine, flat compound DC machine, and under compound DC machine. Three types it is. Over, flat, under. Now how to achieve that over, flat, under compound in the cumulative compound is by adjusting field currents such that we have to check no load voltage, full load voltage. So what is no load voltage? For example, you take this. So right now it is load is not connected. Let EMF induced in the generator is E. And across this load is not connected. Across this you put a voltmeter, and the voltmeter will show you whatever EMF induced, almost same voltage here. This is called no load. The EMF induced in generator under no load condition, that is no load voltage. Okay, let it is some 200 volts for example. Now let us connect a load here. Whenever load is connected, definitely a current will flow here. A current will flow, IL. And based on this current, series flux depends on the load current only, because it is variable here. Series flux only changes. Shunt is constant. Field current almost constant. The shunt flux also almost constant. But series flux mainly variable in this. Okay. So in cumulative, as both the fields are added, whenever load is connected, IL will flow, series flux increases, overall flux increases, EMF induced increases, and the voltage across the load at that time changes. Now this is no load voltage and full load voltage. This is no load. This is full load. Now let us check what is the full load voltage value. So this may be less than 200, or we may achieve this equal to 200, or we may achieve this greater than 200. So these are all possible only when we keep a diverter across the series field winding. So put one diverter here and change the value of this diverter from minimum to maximum value. So during that variation we get these three types. Full load voltage may be more than 200, no load voltage. That is more than 200, less than 200, or equal to 200 also we can achieve by changing this diverter. So this diverter is very important to achieve the three types of compound machines: over, flat, under. Clear it is? So like this we can get in DC compound mainly two types: cumulative, differential, and we can connect in long shunt or we can connect in short shunt. And in order to achieve cumulative three types again, over, flat, under, we need to adjust this diverter in this. By adjusting this diverter, check what is the relation between no load voltage, full load voltage. So in over compound, the full load voltage will be greater than no load voltage. In flat compound, the full load voltage is almost equals to no load voltage, but in under compound the full load voltage will be less than no load voltage. So remember this. So based on these conditions we can call whether it is over compound or flat compound or under compound. Okay. So these are the three types in cumulator. So these are the types, and you have to write these KVL equations for long shunt and short shunt. Okay, same as previous, you apply KVL like shunt and series we written. However, in the same way you write KVL for this one, long shunt and also short shunt. Okay. Now these are the types of DC machine overall, a brief idea on the types of DC machines, how we divided. Based on excitation of field winding we divided mainly two types, separately and self. And again self divided into three types, shunt, series, compound. Again compound divided into some two types, mainly cumulative differential, and again based on type of connection two types, long shunt, short shunt. Long shunt, short shunt also out of this only, cumulative differential. Again cumulative we can achieve three types, over, flat, under, by adjusting diverter across series field such that no load voltage, full load voltage will changes. Based on that three types we have. So this is about the types of DC machines. So this is our today's topic. Try to have a look. If anybody missed, whoever is attended the last, try to listen again from starting so that you will get some clarity on the types of DC machine. So thank you everyone.
2 to 3 pages short notes of each and every subject. Now 2 to 3 pages short notes help in quick revision. If you keep working hard, you will definitely get success in this examination. This is what I followed, and I wish all the best for all the future aspirants. Thank you.
My name is Kuldeep. I have done my BTech from Ambedkar Institute of Technology, which is situated in Delhi, and I have secured All India Rank 1 in ESC 2021 from E&T branch. I took ACE Postal Course, Mains Test Series and Interview Guidance Program in ESC 2020 and ESC 2021.
Hello everyone, my name is Karthikeya Kaushik and I have secured All India Rank 1 in UPSC Engineering Services Examination 2021 from Civil Engineering discipline. For prelims preparation, I took online test series from ACE online platform and used to regularly solve their subject-wise test and full-length test. Then for mains preparation, I solved question banks which were given to me as a part of mains postal program from ACE Online. And then last but not the least, for interview preparation, I followed the interview guidance material which was given to me as a part of ACE Online's interview guidance program.
I am Vinit Kumar. I have secured All India Rank 1 in Mechanical Engineering in ESC 2021. I have been associated with ACE Engineering. I have taken various programs like Lives, main classes, postal study course, test series and interview guidance program. So would like to thank all the faculties of ACE. It has helped me in building my concepts and having my fundamentals cleared. I would also like to highlight that in test series, I have given various mock tests which have helped me in the time of real exam, and in interview guidance program, building confidence in front of interview panel. It has helped me in my success.
Myself Abhishek Kumar Sharma. I have scored All India Rank 1 in UPSC Engineering Services Examination 2021 in Electrical Engineering discipline. Now I divide my preparation strategy into three basic things. The first thing is that you have to complete your syllabus from a basic standard source. The second thing is that you have to attempt previous year question. The third thing aspirant has to do is to solve as many test series as possible. I made 2 to 3 pages short notes of each and every subject. Now 2 to 3 pages short notes help in quick revision. If you keep working hard, you will definitely get success in this examination. This is what I followed, and I wish all the best for all the future aspirants. Thank you.
My name is Kuldeep. I have done my BTech from Ambedkar Institute of Technology, which is situated in Delhi, and I have secured All India Rank 1 in ESC 2021 from E&T branch. I took ACE Postal Course, Mains Test Series and Interview Guidance Program in ESC 2020 and ESC 2021.